Okay, I think we can just start. I'm Noah Yuan, and today I will host myself. Good morning if you are in America. Good afternoon if you are in Europe, and good evening if you are in Asia. I think it covers most of the audience. So today I will talk about the supercurrent diode effect and finite momentum superconductivity. So this work is in a collaboration with Liang at MIT. It will involve our two recent papers. Oh, sorry. So here's the outline. Firstly, we'll discuss the experiments which motivated us for this study. And then we will discuss the spin-off copper superconductors and the finite momentum Coulomb pairs. And then we will mainly focus on the supercurrent diode effect. Finally, we'll give a conclusion and outlook. So our motivation are the two experiments which arises recently about this superconducting diode effect and non-reciprocal critical field. So the device is a artificial superlattice made by niobium, tantalum, and vanadium thin films. So they make this artificial superlattices such that the inversion symmetry is broken. And then if we apply some magnetic field, we'll find that the system can become a diode. Namely, along one direction, the current is normal. It has finite resistance. And along the opposite direction, the current is a supercurrent. So here is the experimental data. So at zero current, at small current at zero magnetic field, we'll find that the system is superconducting with a critical temperature about 4.4 Kelvin. And then when we apply some magnetic field with the same magnitude of the current, we find that the current is just a normal current with finite resistance along one direction. And if we switch the direction, the current becomes supercurrent with zero resistance. And if we switch the direction of the field, the superconducting and normal direction also switches that direction. So that's the supercurrent diode effect they found experimentally. So this effect is essentially due to the fact that the critical current is non-reciprocal in this system. So here is the data of the critical current. We can find that in the presence of finite magnetic field, the critical currents along opposite directions are different. So that's the so-called non-reciprocal. And there's another related experiment on the same device that the critical field is also non-reciprocal. We call it the polarity-dependent. So in the presence of some supercurrent, it's found that when the magnetic field is perpendicular to the current direction, the critical field will be different along opposite directions. While if the magnetic field is parallel to the current direction, the critical field will be reciprocal. So here is the experimental result. Now this seemingly two unrelated results actually two aspects of the same phenomenon. That's the terminology we adopt called the supercurrent diode effect. Now it can be summarized by this phase diagram in the phase space spanned by the magnetic field and supercurrent. So we can find two DOMs for the currents along positive direction and negative direction. inside the DOM, the system is superconducting, and outside the DOM, the system is normal. So if we fix the magnetic field, we'll find that the critical current will be non-reciprocal. There are so plus I and minus I are different. And if we fix a current, then we find that the critical field will also be non-reciprocal, polarity-dependent. So then it's actually two aspects of the same screwed phase diagram. And then we can analyze the symmetries of this phase diagram. We know that under time reversal, magnetic field and the current both change sign. But under inversion, the magnetic field does not change sign because it's a pseudo vector, while the current will change sign. So clearly in this phase diagram, the time reversal is respected, but the inversion is not. So the time reversal is respected because these two DOMs, this green DOM and this purple DOM, they are symmetric with respect to this y-axis. So we find that the symmetries of this phase diagram. And so based on the symmetries, we can propose possible mechanisms for this phenomenon. For example, the simplest one we can think about is the spin coupling plus the Zeeman effect, which so the spin coupling preserves time reversal but breaks inversion. And also geometry plus orbital effect. The geometry, you can prepare a geometry which breaks the inversion symmetry, and also some essays, etc. But in this talk, we'll focus on the first mechanism, which is due to the spin coupling. For example, if we have a Rashba spin coupling, it's usually created by some electric field. For example, in a layer system with two different materials, there will be a potential gradient, namely a electric field. We know electric field will preserve time reversal symmetry, but it breaks inversion symmetry. So it will create an effective magnetic field, which gives you this spin coupling. So before we talk about the role of spin coupling, let's first review the case of conventional superconductor, where time reversal and inversion are both preserved. So for conventional superconductor, we know we have a spin degenerate Fermi surface. And so when we form cool pairs, the total momentum of the cool pair will be zero because we pair a electron with momentum k spin up and another electron with minus k spin down. And so the depairing energy will be zero, and we will create a superconducting energy gap, which is 2 delta. And here is the band structure, the so-called Bogoliubov quasi-particle band structure. So, and then when we apply some supercurrent, we'll make the cool pairs to have some finite momentum. So in the presence of some supercurrent, the cool pairs will be formed by electrons with with unequal momentum. So the total momentum we denote by Q, and it's proportional to the supercurrent. The proportionality constant is the so-called superfluid stiffness. So because now the two electrons in the cool pair, in the presence of supercurrent, they have different momentum. So they will have different energy. And the energy difference gives you the finite depairing energy. And this depairing energy, as long as it's smaller than the energy gap, the superconductivity will survive. And so we have the criteria for the critical current, and that is the depairing energy equals the pairing gap. So it's the critical current is about the gap closing current. And here is the schematic plot for the energy bands under supercurrent. And we find that the supercurrent in this conventional case is reciprocal, because you apply positive current or negative current, the gap closing are symmetric. So that's the conventional case. And if you apply some magnetic field, you find that in the conventional case, the magnetic field just simply split your Bogoliubov quasi-particle spectrum into two. And still, your gap closing current is determined by just the single Bogoliubov band, which is the lower one. And so in general, under in-plane magnetic field, the Fermi surface will be split into two. And this gives you a dependent energy proportional to the magnetic field. And by the same argument, similar to the critical current, we find that when the dependent energy equals to the energy gap, we got the critical field, which is about the Pauli limit. So that's the critical field and critical current for the conventional superconductor. And to summarize, we can plot such a phase diagram for the conventional superconductor in the phase space spanned by magnetic field and current. So this phase diagram is fully symmetric with respect to J-axis and also B-axis, because it preserves time frozen and inversion. So that's the phase diagram. And now let's think about what will happen in the Rashba system. In the Rashba system, firstly, the Fermi surface. We have two Fermi surfaces. And so for both Fermi surfaces are spin split. And within each Fermi surface, the spin configuration is so-called helical. It's perpendicular to the direction of the momentum. And so within each Fermi surface, the time-fold symmetry is preserved. And that's the Rashba Fermi surface. And we have two concentric circles. So we can introduce the two energy scales. One is the spin coupling and also the Fermi energy. The spin coupling is always smaller than the Fermi energy. And to see the how the Rashba system, the role of Rashba spin coupling, let's just consider a limit where the spin coupling is maximized, which is equals to the Fermi energy. So in this case, we just find only one Fermi surface, and that's the case of for Fermi surface states of topological insulator. And we know in the case of TI surface state, when we apply a magnetic field, it can be found that the shape of the Fermi surface is not changed. The size is also not changed. The only change is that the Fermi surface has an overall shift by a momentum proportional to the magnetic field. And the spin configuration along the Fermi surface is still the same with respect to the new center of the Fermi surface. And so when we form core pairs, without magnetic field, the core pairs are formed. We have core pairs formed with respect to the center. And also with magnetic field, the core pairs will also be formed with respect to the center. But now we know the zero momentum is not at the center, but at another place. So the total momentum for the core pair is actually finite. We can find that the total momentum of the core pair is proportional to the magnetic field, like this. And we call this kind of superconductivity symmetric, because it's all the parameters similar to the order parameter of symmetric liquid crystal. And now let's go back to the Rashba system. for the Rashba system, we find that it can be regarded as two copies of Ti surface states, but with opposite helicity. So as a result, when we apply magnetic field, we find that the Fermi surfaces will move to the opposite directions. So for example, in this case, the inner one move to the left and the outer one move to the right. And also because the two Fermi surfaces, now they are closer to each other, you find that in the region where they are closer, there will be some deformation for the shape, and they will become so-called Cartesian overs. So that's the Rashba system under the magnetic field in the normal phase. And in the superconducting phase, similarly, we will expect some symmetric phase. Namely, the core pairs will have some finite momentum. And the core pair momentum is still perpendicular to the magnetic field, but its magnitude is not just simply linear to it. We have to calculate it numerically. And we find that at small field is still linear to the magnetic field. But when the field increases, especially near this polar limit, it will become, its slope will have a change and becomes nonlinear. So that's the symmetric phase of Rashba superconductor. And so this interesting thing will give us a very important expression for the supercurrent. Now, in the symmetric phase, let's apply a supercurrent. So when we apply supercurrent, we'll find that the core pairs will have additional momentum. And so the supercurrent can be written as the momentum deviation from the symmetric momentum. So it can, when the deviation is small, we can always expand it as rho times Q minus Q naught. So this rho is still the stiffness, and the Q naught is just the symmetric momentum we numerically calculated here. So in this case, we find that unlike the conventional superconductors, in this Rashba superconductors, in the expression of supercurrent, there are some contributions from the magnetic field. And so because of these contributions, we find that when we calculate the gap closing current, it becomes nonreciprocal. For example, in this case, if we calculate the gap closing current along the positive direction, we find that it's determined by the Fermi surface, by the inner Fermi surface with smaller Fermi momentum, while the gap closing current along the negative direction is determined by the Fermi surface, by the outer Fermi surface with a larger momentum. So these two are actually different, and this gives you the non-reciprocal critical current. And as a result, we can actually do some detailed calculation and find this phase diagram in this magnetic field and current phase space. We find the phase boundary is kind of screwed. And we can also have the expression for this phase boundary. We find that the magnetic field is the magnetic field part is not changed much, but the supercurrent part has an additional term which is determined by the magnetic field. So that's consistent with our previous discussion.
Can I ask a question?
Yes, yes.
So the current should be zero inside the superconductor due to the Meissner effect or the energy minimum.
Yeah, so in our case, we discussed the 2D superconductor. So in the 2D superconductor, when you apply an in-plane field, the magnetic field can fully penetrate into the superconductor because.
Okay, but even in this case, there can be some phase gradient which compensates. So the total current is 0. There is phase gradient. If you apply magnetic field, then
yes?
it just induces the phase gradient, but not the total current.
No. In this case, the phase gradient is that effect is so-called orbital effect is neglected because the 2D superconductor is so thin that is actually smaller than the London penetration depth, so it cannot create enough phase gradient, and we neglect this effect. There's only a Zeeman effect in our 2D superconductor.
Why it cannot create? So the phase gradient is in 2D plane, so it's it can be.
The phase gradient can be created when your magnetic field is along z direction, is along the outer plane direction. But if the magnetic field is along the in-plane direction, you cannot create enough phase gradient.
That's, I don't understand. Actually, I think that the current should be 0. But anyway, so thanks.
Okay, well, let me continue. So so this is the phase diagram of we calculate for the Rashba superconductor. Now, so we have a parameter describing the screwness of the phase diagram. So this parameter we find that is proportional to the Rashba coefficient divided by the Fermi velocity, and also it has some temperature dependence. So when the Rashba is 0, this screwness parameter is 0, which and then we go back to the conventional case. And for this phase diagram, we can consider the two aspects. In one aspect, we apply some magnetic field and calculate the critical current along opposite directions. We find that the difference, the relative difference between the two critical currents is proportional to the magnetic field. And the proportionality constant is determined by the screwness parameter. And also, when we apply some supercurrent, we can calculate the critical field along opposite directions. And it's, the relative difference is also proportional to the applied supercurrent. The proportionality constant is also determined by the screwness parameter. And this 1/3 coefficient is due to the fact that the exponents of field and current are actually different. So we're gonna further work out the temperature scaling for this critical current and critical field. So the average of the critical field is has a temperature scaling with exponent 3/2, while the difference is has an exponent 2. And also for the critical field, the difference is temperature independent, while the average of the critical field is square root of the temperature. So so now this is just a schematic plot for our Rashba superconductor. When the current and magnetic field are perpendicular, the Fermi surface has a shift along this current direction, so that we have a screwed phase diagram. But if we have, if we apply magnetic field parallel to the critical to the supercurrent, the Fermi surface, the shift of Fermi surface is actually perpendicular to the current direction, and so the current is actually the non-reciprocity of the current is not affected, and so the phase diagram is still symmetric. And as a summary, so we have conventional, for the conventional superconductor case, the current will boost the Coulomb pair momentum, and the magnetic field will just split Coulomb pairs. So, and we can have a phase diagram where the two terms are kind of independent of each other. They're not combined together in this phase diagram. While in this symmetric superconductors, the current will boost Coulomb pair momentum, and the magnetic field will not only split Coulomb pairs, but also boost the Coulomb pair momentum. And as a result, in the expression of the current, supercurrent, you also have a term related to the magnetic field. So this phase diagram is screwed by this inversion symmetry breaking term. This gamma term is proportional to the spin coupling divided by Fermi energy, and also it scales linearly with the temperature. And also we have a angular direction factor, and this theta is just the angle between supercurrent and the symmetric momentum. So in general system with a spin coupling described by the vector g of k, we can calculate the symmetric momentum at small b. So its direction is basically determined by the form of spin coupling. And we can find that in order to make this expression non-zero, the point group can only be in this classes. So for example, if we consider, we can have some examples. In this dihedral point group, the symmetric momentum is parallel to the magnetic field. And in this CMV point group, the symmetric momentum is perpendicular to the magnetic field. And in this D2D point group, the symmetric momentum and the magnetic field, they form a mirror pair. So then in order to realize optimal supercurrent direct effect, we can just apply our supercurrents parallel to the symmetric momentum direction. Sorry. For example, we just discussed the Rashba case with CMV point group, and then we will expect that the supercurrent direct effect is maximal when the current is perpendicular to the magnetic field. While in this dihedral point group, we expect that when the magnetic field and the currents are parallel to each other, the supercurrent direct effect is optimal. And this corresponds to the twist bilayer graphene case, for example. And also in this D2D point group, we expect that when magnetic field and the currents form a mirror pair, we'll have a maximal supercurrent direct effect. This point group can be found in the crystal planes of some cubic system. So, and we just mentioned this twist bilayer graphene. But we all know that in the twist bilayer graphene, the carbon atoms, they have very tiny spin coupling, basically it can be neglected. So, but symmetry-wise, it is still allowed. So what can be the potential mechanism for this twist bilayer graphene to have this supercurrent direct effect? It's actually can be due to the orbital effect. So as I mentioned in answering the audience questions previously, usually in the 2D superconductor, when you apply some in-plane magnetic field, the orbital effect can be neglected because the z along the z direction, the thickness is much smaller than the London penetration depth. But in the twist bilayer graphene case, we find that along the in-plane direction, the superlattice constant is 14 nanometers, and the Fermi wavelengths can be even longer. So due to this enlargement of this in-plane length scale, when we apply a in-plane magnetic field, you can have a large enough area to trap a single flux quantum, so that the orbital effect can be significant. And we also perform some kind of calculations. We find that in this twist bilayer graphene case, when we apply magnetic field, the Fermi surface will have some shift and distortion along the same direction of the magnetic field. So this is similar to the Rashba case, where the Fermi surface will have a shift along the direction perpendicular to the magnetic field. So this may be the potential origin for the potential supercurrent diode effect in twist bilayer graphene. And also, we expect that there may be some supercurrent diode effect in MoTe too, in the TD phase, where the symmetry is very low. And the spin coupling from our first principle calculation is about 5 milli-electron volt, considered large compared with the pairing potential. And also, this effect may be found in the layered superconductors. For example, in this layered structure involving this serum compound indium-5, the layered structure breaks inversion symmetry, and it has been found that when you measure the critical field, when you measure the critical field in the absence of supercurrent, there will be an upturn at some low temperatures, indicated by these arrows. And in other layered superconductor, which is SrTiO, growing in some AT material, it's found that there is also some upturn. Here, the phase diagram is plotted in some unconventional manner. So the x-axis is the magnetic field. The y-axis is the temperature. And so you can see that at lower temperature, the critical field also has a sudden increase. It's just an upturn. And this upturn it can be maybe explained by our symmetric phase. So we can calculate the critical field in the absence of supercurrent for our symmetric phase. We find that around this polar limit, the convexity of the critical field changes. So you see a upturn of your critical field. And this may be a sign for supercurrent diode effect. And also, since in our calculations, we assume that the order parameter is the symmetric phase. Namely, we only have one momentum. So our theory can be applied to the case near superconducting transition. And near this transition, namely along this the critical field along this line, we can calculate this we would call the supercurrent diode coefficient, which measures the non-reciprocity of the critical current. We can find that it has a square root temperature scaling, and also its magnitude kind of increase until near this until it reaches maximum near the polar limit, and then decrease again. So that's the supercurrent diode effect near this near the superconducting transition. But when we try to study the supercurrent diode effect inside the superconducting phase, we will encounter with a problem that either that the order parameter can actually break the translational symmetry spontaneously, and to pick up a multiple Q ansatz. So to determine whether it's single Q or multiple Q, we can calculate the free energy in terms of this order parameters. So we have to include high order term, such as fourth order terms or even sixth order terms to determine whether it's a single Q or multiple Q. So that will be a not a simple work, but nonetheless, recently there is a paper. They showed a numerical study for the supercurrent diode effect by assuming a single Q state in the superconducting phase. So what they find is that near the TC, near the superconducting transition. So this dashed line are from our analytical calculations in previous slides, and these dots and solid line are just from numerical calculation. So we find that near the superconducting transition, we have this. So this delta JC denotes the difference between the critical currents. So we find that the scaling is just T squared near this TC, and also we have they calculate some critical currents and at different conditions. So we just discussed this the supercurrent diode effect in this superconductors without inversion symmetry, without inversion center. So actually, this kind of effect is just a one example of non-reciprocal transports in the superconductors. So it's just a charged supercurrent inside a single superconductor. We can have spin supercurrents and also this heat flow, all kinds of things. And for this, even for the charged supercurrents, we can discuss the Josephson junction case, where we have two different order parameters with a phase difference. So recently there is an experiments on this Josephson junction. So so they also find this similar this supercurrent diode effect. Along one direction is normal, and along another direction is superconducting. And they also plot this phase diagram. So the authors actually give a talk also on this platform. You can check it. So they discuss these experiments, and we can perform similar symmetry analysis for the experiments. So we find that in this case, the inversion symmetry is broken, but also the time force symmetry is also broken. Because at zero current, at zero field, the critical current is already non-reciprocal. So for this Josephson diode, the so-called Josephson diode, recently there's also a paper by Nagausa group. So they did some numerical calculation for such a Josephson junction where the inversion symmetry is broken. And it's found that when you apply magnetic field, these Josephson currents as a function of the phase difference is not symmetric. And so with this slide, I just want to thank you for your attention and thank the organizers to offer this platform for me to discuss our work. And I'm ready for the questions. Any questions?
Can I ask a question?
Yes.
Actually, about 7 years ago, I had a paper on the diode effect induced by the domain wall superconductivity.
Sorry, by what superconductivity?
Domain wall. It's a superconductivity localized near the domain wall.
Oh, domain wall. I see.
In the superconductor ferromagnet structure.
I see.
And also, I think it's by symmetry, it's quite close to.
Yeah. So it breaks the inversion and also time frozen.
Yes. So inversion is just by the distribution of magnetic field, because you have the domain wall. And the time reversal is because there is magnetic field actually. And the current is the critical currents are different in different directions along the domain wall.
I see.
So it's also some example of this diode effect. I have posted this reference in the chat.
I see. So
if it maybe it's
you can just write to my email.
Yeah, I will be glad. So since this topic is become quite popular, maybe it's.
I see.
But anyway, thanks for.
Thank you. Let me see the questions.
Yeah, I have a question. If thinking of 2D materials, the ones that you listed, as far as I understand, are not really of superb quality. So I would expect some inhomogeneity to be present. So basically disorder. Now, thinking about these systems in presence of disorder, I would expect that the critical current will be set by sort of the weakest link. So, in other words, I would expect them to somehow interpolate between the bulk behavior and say Josephson junction behavior, because there's a single point where the critical current density is the smallest. Do you know if there's a way to distinguish macroscopically homogeneous behavior from this kind of percolation disorder response? And do you know if the experiments are whether we can convincingly conclude that the experiments see a homogeneous behavior?
So I think firstly we can estimate the mean free path from the normal resistance, right? And also we can let me see. In the superconductor case, we also have some way to estimate the mean free path, but it depends on our theory. Nevertheless, in the normal phase, we can always extract the mean free path data, and then we can just know whether it's in the clean limit or dirty limit or just some disorder. So here our theory is just the clean limit. Well, I think there's a question by Banabil Park. In the Josephson junction, how is the time flow symmetry broken in the absence of an applied field? I think you just sorry. I think what you mentioned is this experiment. Actually, currently, we don't know why the time flow symmetry is broken. It may be spontaneously broken by the pairing itself.
If I may continue also about the same system.
You mean this?
So yeah, because I also was wondering, and there's a recent recording by the author in the same seminar series. So wouldn't spontaneous time reversal symmetry breaking also show hysteresis, as you say, reverse the supercurrent or reverse the magnetic field? If it's spontaneous, I would expect at least to see some kind of switching behavior, and here it does not seem to be the case.
Yeah, actually, the experiment is quite strange, because it seems that when they measure the difference between the critical currents, it does not have a kind of area scaling. So it's not proportional to the area of the sample. So the result is kind of strange. I don't fully understand it.
All right, thanks.
Thank you.
I have a question.
Yes. Yeah.
So about bilayer graphene, you said because of orbital effect, which can cause similar effect, right? In bilayer graphene.
Right.
So that means spin orbit coupling is actually not necessary ingredient for this phenomenon.
Right. So in the twist bilayer graphene case, the valley plays the role of spin. So indeed, spin coupling is not the key ingredient. The key ingredient is the symmetry. As long as the symmetry is just in these point groups, we will have this kind of superconductor effect. Yes.
So then in the bilayer graphene case, which direction do you expect to have this non-reciprocal effect?
Right. The currents will be parallel to the magnetic field because
both in plane.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
I see. Thanks.
Thank you. Any other questions?
Can I
Yes.
actually return to this question about the current, about this orbital effect? So you could you please explain? So you search the other parameter in the form which has this phase gradient q, momentum, but so. Isn't this Q should be determined from the condition that actually the energy is minimum, and the minimum of the energy means that the current is zero?
Yeah. So yeah. I know what you mean. So sorry. In this case. Oh, sorry. You mean in this case, when we apply magnetic field, in the equilibrium case, the supercurrent should be zero, right?
Yes.
Right. I think we agree with each other, because when you set Q equal to Q naught, the current is actually zero.
I see. Yes, exactly. Okay, thanks.
Yeah.
Hi, Nora. I have a simple question for you. Why when Q equal to Q0, the current is zero when in the absence of magnetic field? Why that?
So because the system is in the ground state, and the ground state should be equilibrium, and so it's kind of how to say, it's free energy with respect to external field. The derivative of the free energy with respect to external field will be zero, and the current can be written as a free energy derivative with respect to the vector potential. So the current is zero in the ground state.
Okay.
So any other questions?
No, but thanks for the presentation.
Okay, yeah. So thank you for your attention. There's what? Oh, yeah. Thank you. So that's the end of the talk. Thank you for coming. Bye.